Okay, let's get started. Hi, everybody. Very responsive crowd. Fantastic. All right. I'm Mike Onepo. I'm a program manager on the DirectX team, so I'm responsible for I was actually part of the Windows 7 team. We helped ship Direct3D 11, which I'll be talking about today. And I also helped with a couple of the other features in Windows 7 for graphics that I'll be talking about to make sure that we understand the full platform and everything that's available. Just a quick agenda, talk about some improvements we made on Direct3D for Windows 7. Just a quick review of Direct3D 10. Understanding how we extended the platform in Windows 7 to make it so that Direct3D 10 could be used for more different types of reach. So the idea of being able to target more and more hardware that's available on the market today. As you may remember, Direct3D 10 was tied to Windows Vista and Direct3D 10 only parts. We've changed that. We've expanded it out to a much broader set of hardware scenarios. I'm going to briefly do a review of HLSL and shaders, and then finally I'm going to step and dig really into the Direct3D 11 demos and the Direct3D 11 technology that we have. In PDC 08, we talked a lot about what we had to offer. We announced everything that was available for Direct3D 11, so sort of what it can do. Today I'm going to talk more a little bit about how it does it and how you can go and use it. There's an additional feature, quick review of the two features that I am going to talk about in Direct3D 11, which are multi-threading, so improved performance using the CPUs that you have on your machine to feed the GPU more data. And I'll be talking about tessellation, turning higher order primitives like curved patches, curved lines into triangles on the GPU for improved quality. There's an additional feature of Direct3D 11 that I'm not going to talk about today called Direct Compute, which is it's available in the Direct3D 11 runtime. It's meant for general purpose programming on the GPU. The reason I'm not going to talk about it is because we have a whole talk devoted to it tomorrow at 11:30 a.m. By Chaz Boyd, my colleague who's actually sitting in the audience today. And he's going to be going into some great detail about exactly what this has to offer and making it so you can use these incredible GPUs that I'm going to be talking about today for things other than graphics, or to extend the graphics platform in ways that are pretty innovative and pretty awesome. So I encourage you all to check out that talk. It's some pretty great stuff. In addition, we have the Direct Compute hands-on lab that is running currently in the big room. If you go to the Windows section, you'll see a bunch of computers. There are special ones set up with DirectX 11 hardware that you can play with right now, particularly to try out Direct Compute scenarios. So I encourage that you go and you check that out. Okay. The first thing I want to talk about when we're looking at Direct3D is understanding when Direct3D might be important to you as a developer. And the key point I want to communicate on this is that Direct3D is a low-level programmable rasterizer. It is meant to give you the best performance you possibly can without a lot more. It's very bare bones. What we're trying to do is give you the opportunity to really dig your fingers down to the metal and get at the hardware that's available on your machine. To do that means you have to pay a little bit more in code. You have to write a little bit more. But each line of code that you have is something that you can customize. So you can throw away things you don't need. You can tune it down to the exact code that you need it to do so that you're exploiting that GPU as much as you possibly can. So we really recommend the scenarios for using Direct3D are when you need the utmost control over the GPU for high-performance, high-quality 3D. The history of Direct3D sort of shows this. For those of you who are familiar with the platform, it originally was really meant to be a game technology. It was this idea of being able to render 3D graphics for games. We've since expanded this platform tremendously to be any situation where the graphics card is needed, but it's an underlying platform that really is meant to exploit every possible flop that you have on the GPU. Okay. So the first thing on the agenda that I want to talk about with Direct3D is going to be a quick Direct3D 10 review. Who here has seen this diagram before? This is the Direct3D 10 diagram. About 10, 12 of you? Okay, great. So I'm going to quickly walk through this diagram to help those who aren't familiar with exactly how Direct3D 10 works. Make sure we understand this, because a lot of the features I'll be talking about for Direct3D 11 build on top of Direct3D 10, so it's important to understand how this works. Hopefully, also, I'll give you a good understanding of exactly what I mean by bare bones, exactly what I mean by providing you control over the system, and what you can do to optimize. So let's walk through exactly what the purpose of this pipeline is, and it is to provide a way of converting points, lines, and triangles into pixels, by pushing it through a bunch of different stages that allow you to do a variety of different transforms of the data into different pieces as you move along. And the first thing that's going to happen is it's going to go into the input assembler. The input assembler takes every single point, line, and triangle that you feed into this pipeline. So the idea is you're sort of feeding stuff into the input assembler, and then out the bottom you get some high-quality image. You feed these primitives into the pipeline, and this will take all that information in a fixed function way, in other words, a way that you can't write code to control it. You can't write a shader to control it. It'll take in these vertices, and it'll do some duplication of the data, essentially. And this is useful when you want one model that you want to render millions of times, and that's called instancing. You want to render, say, a leaf, but you want to render it millions of times so you can do all the leaves on a tree. Or this concept of indexing, which is essentially a form of compression, where I can provide just a list of vertices and then reuse the vertices by, instead of actually refeeding the entire vertex and all the floating point values for it down the pipe, I can just say, I actually want vertex number 7. So you index into the array. So all the triangles come out of the input assembler. It breaks that up into the 3D vertices that you have for all of your models, and it passes each one of these onto the vertex shader. The vertex shader was designed back in the Direct3D 9 timeframe, actually, Direct3D 8 even, to provide a way for you to do transformations on the entire model. Most of the time, those transformations are very simple. Things like converting the triangles from the 3D space that they're sitting in to the actual 2D plane of the screen. So that's the perspective transformation or the view transformation. Additional things that you might want to do, and the reason why we've made this stage programmable or customizable, you can write code to actually define exactly how this code executes, is for things like skinning. So being able to take what would otherwise be a neutral pose of a model. Normally we say like for an animated character, it's with their arms sticking out. And then you have some information about the bones in the system. You can actually use the vertex shader to figure out how to reposition those bones and then therefore reposition the model. So this can be something very simple, like just doing the transformation to get everything into the right coordinate frame for the screen, or something more advanced, like doing character animation. So then we move down to the geometry shader. This was introduced in Direct3D 10. And the idea behind this was to have an ability to operate per primitive on the model. So a primitive is a point, line, or triangle. In the event of a triangle, this will get every single vertex of the triangle, so it'll get 3 vertex values. And it will allow you to do any operations you need. And there are examples of things that you could do with this. One of the coolest things about the geometry shader is you might just want to transform it a little bit, maybe grow it or shrink it so you could scale the whole model. Another option you have is you can actually cull it from the pipeline entirely. So if you figure you don't need the triangle that's passed into the geometry shader, you can throw it out. Or you can add more. Why would you want to add more geometry into the pipeline? The design of the geometry shader is for things like, say I wanted to create a fur onto the model dynamically. The way that I could do this is I could look at the triangle that I have, I could figure out which way the hair should be sticking out, and start generating a simple amount of geometry in order to provide, say, spiky hair or maybe some shells over it to provide the soft fur effect. We actually have a sample that does that in the DirectX SDK, which I'll be providing a link to later, and I encourage you to check that out. There's some really cool stuff you can do with the geometry shader. Okay, so we've done all this transform of every single triangle. The next stage that it will go into is the rasterizer, which takes each triangle and actually converts it into pixels on the screen. So this will figure out the position of every single pixel that triangle needs to have on the screen. Then for each of the pixels that rasterizer has figured out where the position is and everything, it'll actually go and execute the pixel shader. And this is what actually does the real meat of a lot of what graphics processing is, which is figuring out the color values for each pixel on the screen. The most common operation that this will provide is lighting. So the idea of being able to figure out where the lights are in the scene and being able to do some math to figure out exactly how bright that pixel should be based on the lights that are available. Another common operation is texture mapping. This is really where the texturing pipeline works a lot. You can see texture as an input in this pipeline. And that's where you get the ability to map a texture onto the geometry that you're rendering. So now we have the colors that were provided. The last step is the output merger. This is another fixed function step that does things like blending those pixels onto the screen or figuring out whether or not a pixel is visible at all by doing occlusion culling. Another term for this is depth testing, where you're storing a depth value, and if there's a pixel that's already rendered to the screen that's closer, don't even bother rendering this one to the screen. Okay, so that was just a 5-minute crash course in exactly what Direct3D 10 can do. You can see we have a lot of places where you can customize this pipeline. Some things I want to note: you can turn off the geometry shader entirely if you don't need to use that at all. So you can pare down your pipeline to only the things you absolutely need. And another thing I should note about this is that the inputs and outputs between each of these stages are fully customizable. So if I don't even want to be dealing with 3D coordinates, I can actually be passing 2D coordinates through all these, or one-dimensional coordinates. Why I'd ever want to do one-dimensional rendering, I have no idea. But it's possible. We make that something that you can do. So you can immediately see the kind of customization you can do with the Direct3D pipeline. So what did we add in Windows 7 to make this system work? And again, I mentioned that on a larger set of hardware. And previously, I mentioned that for Windows Vista, Direct3D 10 was tied to Direct3D 10 class hardware, which was at the time a relatively new set of hardware that was available. In Windows 7, we decided that we were going to make Direct3D 10 the baseline operation for graphics, the baseline library for graphics across the board. So new technologies that we've been talking about since PDC 08, including Direct2D, which I gave a talk about yesterday, are all built atop Direct3D 10.1. In order to make this something that was easier for the developer to use so that they didn't have to tie themselves just to Direct3D 10 hardware, we recognize that there's a huge market of computers out there that might have Direct3D 9 hardware or might have no hardware at all. So let's take each one of those cases really quickly and understand what we're doing. In 9 class hardware scenarios, where the user's machine only has a Direct3D 9 class card, we have this idea of Direct3D 10 level 9, which essentially takes the Direct3D 10 API, the diagram that I just showed you, and maps it onto Direct3D 9 hardware. Who here has ever used Direct3D 9 to write an application? OK, a bunch more hands. Very cool. Who here knows or has suffered from the problem of caps, or capability bits? So this first bullet point should be familiar to you. The idea that in Direct3D 9 is very, very granular what the card couldn't do. We made that available in this big database that you could query called the capability bits, or caps. This allowed you to figure out exactly what the card had available to it and made it really hard to program if you needed some specific feature. Let's say you wanted trilinear filtering. You could check the bit to see if it was there. If it wasn't there, suddenly you would have to change your code path to make sure you did the right filtering. It was a mess. People worked pretty well in this, but there were a lot of caveats, and people got caught up in this. So how do we solve this problem to make it so that as we move to Direct3D 9 hardware to Direct3D 10, we avoid this? And what we chose to do is we grouped cards into classes. And we created 3, feature levels 9.1 through 9.3. And the important thing to note about each of these feature levels is that, and here's an example of some of the ways that we delineated each of the feature levels and some example cards, is that each one is a strict superset of the next, meaning we don't emulate features if they're not available on that card. We simply remove them, but we do guarantee that as you step up in feature level, you have all the features before. Why is this interesting? This is interesting because if I choose to step up a feature level, I suddenly don't lose things and have to suddenly create whole new code paths. I simply exploit the new available features that I want and make a better program when I need it. The alternative is that I could choose the lowest level, 9.1, write my application to that target, and every higher target will emulate it. And when I say emulation, it just simply means that it will act the same way, but get great performance in the process. So if something fails in 9.1 on actual 9.1 hardware, but you run it on 10 hardware, it'll still fail, but you won't get a performance penalty. So this is really great for development in the sense that testing becomes really much simpler. You can reduce your test matrix just down to the feature levels that you need and test the features according to the feature level. So how does this work actually in code? And one of the things that I take pride in a lot of the code that I have on these slides, and if I'm wrong, please tell me, is that you can take the code off the slide right now and you can throw it in your application to try this out. So this is actually code to walk you through exactly how to create a device in Direct3D 10.1 that will be the best possible based on the graphics card on the end user's machine. So the first thing we need to do is create an array that says every possible feature level that we might be interested in. And I do this in descending order. So the top one, ascending order. So the first one in the list is the best one I possibly want, and then all the way down to the least. So we have this array. It's called level attempts. How do we use it? Well, we can loop through create device. Create device will fail if you provided a feature level that the graphics card can't support. So this is pretty straightforward. I just roll through until I get one that works. Once I get one, I'm great. Break out, and I have my device, and it's ready to go. A couple things to note about Direct3D 10 Level 9. It's also accessible through Direct3D 11. So that means that the Direct3D 11 runtime can support hardware all the way from the new ATI card that I have in the box for my demos today, this new blazing card that Mike Angiulo showed in the keynote, all the way down to 9.1 hardware, so things that were released back pre-Windows XP. So we have this huge gamut of hardware that pretty much defines almost every single PC on the market today. But what if you have no graphics hardware whatsoever? We have this idea of WARP, which stands for Windows Advanced Rasterization Platform. And the goals for WARP were to make a software rendering system for when you didn't have hardware on your machine, or when you wanted something that was just running on software because you didn't want to even look at the graphics card, that was 100% conformant with the Direct3D 10 spec and was really, really fast. The way that we tried to target fast was, we believe it's fast enough for most mainstream scenarios. The most important thing to note is that it scales really well with the number of cores in your system. So as you have more and more cores, you have a quad core, you have an 8-core, it will use those cores to the best of its ability in order to render really great high-quality scenes. OK, so an important thing to note about this is that we did a lot of testing against applications, particularly games and CAD software that were doing high-quality Direct3D in order to make sure that we met these goals. OK, so now we understand how the Direct3D 10 platform works across all these different things. How does this work when I don't have hardware at all? Well, I can call, if that previous code that I've written fails completely, I can then just call create device with create driver type warp. And this is guaranteed to succeed. You'll note that the feature level mechanism is completely different from this. I can pass this flag in independent of that, which means that warp can provide any single feature level you want, say for testing. Quick review of what shaders are, for those of you who aren't familiar with them. The reason why I put these slides up in any deck that I have is that I really want to make sure people understand shaders. They're really the heart and the soul of modern graphics programming. There are stages in the pipeline I showed before that are programmable, meaning that I can write code to define exactly what that shader stage does. So a shader is exactly that. It's the script that tells a programmable stage what calculations to do to achieve a result, something like a material in the pixel shader's case, transformation in a vertex shader's case, that sort of thing. We choose HLSL as our programming language. It's sort of C++-like programming language. It has a huge number of convenience features that are really meant to exploit the hardware. Things like texture sampling are made very easy in HLSL in a way that would not be available in something like C++, to make this as convenient as possible and to match the feature set that's available. Important thing to note are there are no pointers. There's no concept of arbitrary memory access in Direct3D. We very strongly type our memory to make sure that you're doing the right thing from a performance standpoint when you're accessing your memory. So this is an example shader just to show exactly what the code looks like. For the most part, it looks like C or C++. You can call functions, you can define functions, that sort of thing. You'll note a couple small differences. I have this idea of a vector type, something that can be multiple floating point values. So in this example, I have both a float2 and a float4 that I define. Another thing is this idea of this would actually be a pixel shader. This would actually be the code in a pixel shader. So svtarget defines that the float4 value that I return from this means the color that I want on my render target when I'm done. OK. So let's dig into Direct3D 11. We talked about the Direct3D 10 pipeline. We understand all of the, we've done this review of everything. What did we add for Direct3D 11 to really show off this great stuff that Mike Angiulo showed in his demo with hardware? The first thing I want to talk about is multi-threading. And before I really dig into the nitty-gritty of what multi-threading is, I want to understand why. I want to help you understand why we did multi-threading. Multi-threading is to answer the problem that while we have these great GPUs that are scaling, and we had a pipeline like Direct3D 10 that could target them, we realized that the majority of people who are writing applications, when we went around and we looked at ISVs who were writing applications, they would normally have this huge multi-threaded application parallel app that had one thread that was actually feeding the graphics pipeline. And that would often be a bottleneck. They'd actually be doing a lot of work to set up all of their scene on a single thread and sort of be waiting on that thread to finish, and the GPU would only get its data from there. So we asked the question, what can we do in situations where you have multiple cores in your machine, and you want to be feeding the graphics card with more cores? We broke it into two problems. The first problem is the idea of asynchronous resource loading. Being able to allocate resources like off-screen textures and vertex buffers, shaders, that sort of thing, was not thread safe in Direct3D 10. Or at least when you tried to make it thread safe, it would not be very fast. So this was one of the first problems we wanted to solve, was this idea of making it so that you could go and create resources across multiple cores. The other thing we wanted to touch upon was actually feeding actions down to the graphics card, feeding draw commands or state submissions, and spread that work out, because there is work on the CPU to get that all set up before it gets pushed down to the graphics card. We wanted to get that as fast as possible, too. So we did two things to the architecture to make this work. The first thing we did was we divided the Direct3D 10 device into 3 items for Direct3D 11. The first one is the idea of the actual device, which is meant for creation and destruction and management of resources. Pretty much this is exactly what it looks like in Direct3D 10. Creation and destruction of resources is identical. The key difference is it's now free-threaded. I'll talk about it in a second in more detail of exactly what that means. It's actually a pretty simple concept. You can go and use this device at pretty much anywhere. But in order to touch the problem of getting execution to happen across multiple threads, we had to create 2 other objects, the idea of an immediate context and a deferred context. The immediate context is your single primary device. It's the thing that actually will execute calls onto the GPU. And the deferred context is something that can allow you to batch up execution for later execution on the immediate context. So before I get into details of exactly what that means and why that helps you with CPU distribution, I want to quickly talk about the idea of being able to use asynchronous loads. And this is a pretty easy concept. It's that you can use multiple threads using this device object to be sort of setting up the next thing that you're going to render by creating all the resources and doing all the hard work while you're rendering using a preset set of resources that you have. So there's nothing incredibly complex about this idea, but it's really freeing. You can go and do a lot of management of your resources on multiple threads. When we're talking about this idea of deferred contexts, sort of walking through how you would use it, you can create many deferred contexts, and each one is not going to be thread safe, so you have to tie each one to a different thread. And when you issue commands to it, unlike the immediate context, which will feed those commands immediately down to the GPU, the deferred context will start to collect up a command list. And this command list is something that allows you, that is something that you can execute later on the immediate context. A couple important things to note about these deferred contexts is because they're sort of deferred, you can't really do a lot of stuff to modify memory on the system. We pretty much have turned off the ability to do any kind of read back of data from the GPU or even a download from the GPU. And examples of this are queries and resource locking, because we're batching this up for later. So what do I mean by later? Important point to note is that we do provide the lock with discard case, because that's something that the GPU can defer to later. So let's look at this diagram again. We're sort of going horizontally across the slide are all my different threads. And the first one, the first thread I have, has the immediate context that I might be rendering with. And then I create a couple of these deferred contexts on separate threads, and I start issuing commands into command lists on the deferred contexts while I'm drawing using the immediate context. I can then take each of these command lists that were generated and execute them one by one on the immediate context. So at the end of the day, I do have to be serialized. I do have to execute everything on the immediate context. But the trade-off is now I've done all that draw primitive work across multiple threads. So you can imagine how this can scale up. As I do more work on each different thread, I'm reducing the amount of execution work I need to do on the immediate context. So this is a big win from a CPU standpoint. A couple notes about exactly how this works, some caveats to make sure you don't shoot yourself in the foot. Command lists are optimized for single use. When you're done with a command list, it's best to throw it away. This is really because we want to make sure that all the work of batching that all up is something that is encapsulated at each frame render time. No state is inherited from the immediate context. This is really to make sure that there's no ambiguity about what state might be set on one of these deferred contexts. Meaning if I go and initialize a deferred context from an immediate context, no state will be transferred from it. You get a blank slate of everything that you have on the deferred context. This is to make sure that it's clear exactly what state is set in that command list. You can inject dynamic state by using resources. Because resources themselves are sort of a different concept from this execution model. Remember I said it's on the device. You can change those resources and use that in a deferred context. I'm not going to go and encapsulate this. And this makes sense, right? I have the resources in one place. I actually do my execution and I queue it up. So you can get a good model where you're rendering maybe slightly different resources from frame to frame, but you're still able to use the CPU batching model. You can't go the other way either. Once you execute a command list on an immediate context, the state will not get recorded into the immediate context. And this is to allow you to use the immediate context like you would a deferred context where there was no deferred context being executed on it. So this allows you to make sure that there's absolutely no ambiguity on the immediate context of what state should be set. So we always talk about the fastest performance set is to reset the immediate context state after the command list. The runtime will do this. It will reset the immediate context state after the command list execution, and then you'll be able to execute these back to back and not worry about what state is being set or not, because you already know what you've set because you actually had to do it yourself. The Direct3D 11 runtime runs on Direct3D 10 hardware. Like I said, it could target everything from the Direct3D 11 card down to Direct3D 9. So because of that, you now have the ability to do multi-threading across Direct3D 10 hardware. A couple notes about this. The runtime will support it, but you can get further optimizations and further performance improvements from this when the driver also opts in. So the Direct3D 10 driver has to be updated to support some of the Direct3D 11 features, specifically multi-threading. For the most part, drivers are picking up this support. So this is really something that you are going to see. And it works on Windows Vista too. I'll be talking about this, and I'll be talking about exactly how you can get Direct3D 11 on Windows Vista, but you can get it. An important thing to note about driver support in Direct3D 11 is that there's a way to check it. You can actually go and, once you've created a device, you can ask that device whether or not the driver supports it. It's hardware support for multi-threading, so you can understand the performance implications of using it. OK, so that's multi-threading. I really want to spend the rest of my time. I have about half an hour, so I'm going to use pretty much all that time to talk about tessellation, which is a pretty awesome feature. We showed this at the keynote, which we showed a demo of a game engine that was running using tessellation, and I have some really cool demos I want to show that can. This really shows some of the great exploitive power of the D3D11 runtime. But the first question I want to answer is, why would you want to be tessellating in the first place? And sort of the easiest answer for this is as a compression system. In current way that a game actually renders something like a model, let's use this sort of guy in that neutral pose I talked about before. The way that the models are generated today, because the pipeline can only consume triangles, the art pipeline involves creating the model using some kind of higher order primitive, something like a subdivision surface or Bezier patches, curved systems, and then at the last possible second, it's converted into triangles. Into a lot of triangles. In this case, it ends up being about 5.5 megabytes worth of triangles in this specific model. And this is actually a model we ripped off of a tessellation sample we have. So we look at this model, and then we look at the original asset that was used to generate this model, so that those curved surfaces. Something that looks like this, sort of a low-order sub-D mesh. So subdivision is this idea that we can take this mesh and start dicing it up repeatedly with a bit of a sort of averaging algorithm to get a smoother mesh later. So this is exactly how the art pipeline might generate this content in the first place. And this is 130 kilobytes. Wouldn't it be incredible if we could load this down onto the graphics card, meaning faster disk I/O time, because it gets loaded off the disk into memory, then download it onto the GPU faster, because now we've loaded fewer vertices. And then at the last possible second on the GPU, then do the conversion into this high-quality model so that we get a performance improvement from a bandwidth perspective, but we still get the same result. That's the motivation. One of the biggest pieces of motivation around tessellation is this idea that just by reducing the memory that you're operating on, you can get significant performance improvement by delaying tessellation to the last second. So there are more reasons why this might be available, not just from a memory perspective, but when you delay that tessellation, that conversion into triangles, into the last possible second, you can also get this opportunity to figure out what the right triangles are to draw. So if I have the model really far away from me in the screen, it's only taking up, like, say, 8 by 8 pixels, something really far, I don't have to tessellate that really high and get all those triangles. I can just use the lowest level mesh. And then if it's something that's very, very close, I can really tessellate down just the sub-piece that might be viewable and get that really high quality. We call this continuous level of detail. And you can do that on the GPU because you know exactly where that model sits at the time. And then things that had to operate at the vertex level. Remember I was talking about animation, the concept of being able to use the vertex shader for animating? Being able to use that at the control mesh level, this idea of the low resolution mesh, suddenly gives me a huge performance improvement because I can operate on a fewer number of vertices. Other things that require operations on the vertex level suddenly get cheaper too. Examples of this are physics simulations, things like cloth or collisions. So how did we design Direct3D 11 to address this? So this is the Direct3D 10 pipeline. I showed it to you before. If you sort of look between the vertex shader and the geometry shader and then watch this, we added 3 new stages into the pipeline: the hull shader, the tessellator, and the domain shader. And this is pretty much what we provide to make it so that you can do this tessellation. So from the top of the pipeline in the input assembler, we now accept points, lines, triangles, and 3 new types of primitives: concept of a tri-patch, a quad patch, and a polyline. Each of these different primitives has essentially a concept of its topology, so whether or not you're triangular but curved, whether or not you're square but curved, or a line but curved. Lines are interesting for cases like, say, hair or 2D tessellation, where you want to just be drawing outlines. But the important thing to note is that each of these primitives accepts an arbitrary number of control points. So I could just, and those control points are completely user-defined. So you as the developer, you choose what those control points mean. In the case of a Bezier patch, for, say, the triangle, this would mean each of the endpoints and then a bunch of control point positions that define the curvature in between. But you can imagine that you could go and define your own scheme. We don't go that far and say what the exact schemes are, and you'll see the programmability that we have that enables that. So once these are fed into the input assembler, they're passed into the vertex shader. I'll be showing the pipeline in a second so you can sort of get a visual of this, but I want to walk through exactly what the hull shader, the tessellator, and the domain shader do. Once it's passed through the vertex shader and transformed there, we have this hull shader which operates on a per patch, or each primitive that is being passed through the pipeline. But the code that you write executes per control point that you have in your list. And the purpose of the hull shader is this idea of a basis change. And this is essentially a place for you to have the opportunity of converting your geometry from one type of patch or high-order definition system to potentially another. What would be an example of this? Well, let's say I wanted to take something that was a high-order primitive like a Bezier patch, and I wanted to convert it into something that was much faster for me to compute the actual curvature on later in the GPU to get a performance improvement. Here would be my opportunity to say, reduce the number of control points to a smaller number of control points, or something like that. There's a specific basics change that I'll be talking about in a second, which is the subdivision surfaces I've been talking about before. I'll be going into some more detail, and I'll be talking about how we use this stage to make those really fast to render. The other thing that the hull shader does is, after it's computed all the control points, it has a special function that is executed that allows you to figure out exactly how much the patch should be broken up into triangles. We call these the tessellation factors. And it's actually pretty powerful. It's not just one big, how much should I dice this up, like horizontally and vertically with one value. It's actually per edge, and then a bunch of values for the interior tessellation as well. Why do we make it so granular? Well, the idea is that the observation is that the patch could be really long down the screen. It could be feeding a very long sort of perspective transformation. So far away, you might want low tessellation, but very up close, you want very high tessellation. We enable those scenarios. Once the data is done with once the control points have been transformed using the hull shader, those tessellation factors that I referred to are passed on to the tessellator. And the tessellation engine is actually a pretty simplistic concept, where it just takes a sort of archetypical patch, something that's sort of sitting in a 0 to 1 space in 2 dimensions, and breaks that up based on the tessellation factors that you have, figures out what the triangles are, and then for each vertex, it has some coordinate. Essentially, we call this UV space, from 0 to 1 and 0 to 1 for a quad patch. And it computes each of the values for the vertices for that. It has no concept of what the control points might do, but it does provide the actual data for what the patch should be broken up into. There are a lot of different partitioning schemes that this has available to it. I'll be demonstrating a couple of them in a sample later, but the idea is that you can control exactly how it starts to break up the domain based on those tessellation factors. An example of this would be whether or not you want it so that as you slide those values up, they're floating point values, you want to make it so that it smoothly transitions and rolls the tessellation in some smooth way to avoid sudden snapping. But in certain situations where your models aren't moving a lot, you might actually want it to be very fast and just integer-based, so it just snaps to the right thing. So there are a bunch of different partitioning schemes, and I'll be demonstrating those in a second. Finally, the data from the tessellation engine that I just talked about per UV coordinate that it's provided, it will execute a domain shader that will take in that UV coordinate and all of the control points that were outputted from the hull shader, and it will output some actual space position, which is the actual position in 3 space of where that point should be. And now we have all of the data to figure out exactly where all those triangles should lie in 3D space. We've converted that patch into a tessellated set of triangles. So to help you with sort of a visual aspect of this, I'm going to walk through the pipeline and sort of show exactly how this works. So as your input, you might get some patch. This includes your endpoints and maybe some control points that you have. The vertex shader is going to convert that into something that actually is in screen coordinates. Again, it's in world coordinates. The vertex shader can convert it to something that's actually on the screen, so some kind of transformation. Excuse me. The hull shader does some kind of basis change, converts it into something that you think will run faster on the GPU, and I'll get to an example of that. Then the tessellator kicks off, and it takes the archetypical domain, in this case a very flat triangle, and dices it up into triangles. And then finally, all of that data is merged together in the domain shader to figure out the exact positions of the final triangles. Hopefully that helps sort of visualize exactly what this pipeline is able to do. So I want to give a demo. And the machine I have today is, I'm very excited to show off an AMD part, the new AMD DirectX part. And what this demo is that I'm going to show you is a really simple Mobius strip being drawn using the tessellator. And this is all in hardware here. I'm actually going to go to full screen so you can see this really well. And so this is a smooth surface that's being rendered using a tessellation engine. If I turn on the wires here, you can see exactly what the tessellation looks like. And as I slide this patch division value, you can see it breaking it up into further triangles as we go. And we can get this really high into this very smooth surface. If I turn this off, you can see it's really smooth. And if I turn it off, you can start to see some of the old artifacts that we had in Direct3D 10 pipelines with low geometry. You can see these sort of jagged edges start to go away as I increase the quality of this system. Now, an important thing, you notice these 3 buttons down here. These show these different partitioning schemes that I have available. Right now, I'm an integer, and you can see it just, when a triangle is ready to be inserted into a row of triangles is ready to be inserted into the tessellation scheme, it jumps it in. Well, I can choose one of these fractional systems, which will start to ease them in by expanding them out on edges. This is really cool because what it allows us to do is, as the model zooms out, I can introduce geometry in a smooth manner so that you don't have this sudden jump as the model comes in. It sort of smoothly interpolates the values as it comes in. That's really powerful. Okay, so we have this demo. I'd actually like to look at some of the shader code for this, so I can show you that I'm not just hand-waving this. This is actual code that you can walk through. And what this will hopefully show you is I'll show you exactly what this code looks like for each of these different shader stages that I have. So here's my code for my HLSL. And immediately you can see this looks a lot like C. You have comments, you have defines, you were defining a bunch of different control variables and so on and so forth. And the first thing that you're going to encounter, and this is a pretty common layout for exactly how an HLSL file looks, this is one conglomerated file for all of the shaders in my entire program, which is pretty great. Just one file. I can share data, so on and so forth. The first thing that we encounter is this idea of a constant buffer. A constant buffer is a special set of variables that I can feed into any single shader stage that are sort of the parameters of rendering. They don't change when you draw, say, when I'm drawing that entire Bezier patch. In the example that I'm showing here, none of these variables change for any pixel on the screen, for any triangle. They're all the same for that entire execution. And there are 3 variables that I actually use here. One is a matrix, which defines the actual transformation from 3D space of these patches into 2D space of the actual screen itself. So that does all the transformation itself. And then the next 2 values are some information. The next value is information about where the camera position is. And this will become useful when I'm trying to figure out the shading for the model later. The final value I have here is a floating point value that's called tessellation factor. Can anyone guess what this is? This is that slider that I was pulling back and forth. Essentially, we're just feeding that value directly to the GPU. We're not doing anything with it on the CPU. We're doing all the computation on the GPU, which is really awesome. So the next thing you're going to see is you're going to see the vertex shader section. And this walks through, I'm going to walk through exactly what all this data is. Commonly, the way to define your inputs and your outputs from any shader stage is through a bunch of structures. The first structure is pretty simple. It's just the position of each control point that you have. So the vertex shader input is a single position, which is the control point, and the output is going to be another position, and it might do some transformation. In this case, it's just a pass-through shader. We're not doing anything. We're just taking the input position and feeding it to the output. So this is what we call a pass-through shader. It's doing the minimal amount of effort it needs. So then the next stage we have is the hull shader. And we've prefixed everything with VS, HS, so that it makes it clearer to read. And there are two types of output, actually, from the hull shader, like I mentioned before. The first is this idea of each control point that is being passed into the hull shader. The second is the idea of things that are constant to the entire patch, like these tessellation factors that I have. So I have two structures. The first one is all of my tessellation factors, and you can say I have 4 edge factors, like I mentioned before, one for each edge, and then finally some inside tessellation factors, which define exactly how much I should break up the interim triangles in the center. Then the second structure is the output of the hull shader per control point, and in this case it's very simple. It's just a position. And then here's a function that defines the computation of the tessellation factors itself, that first structure that we provided. So the input is all the patch information, and the output is just the tessellation amounts. And you can see that what we're doing is we're setting every single value in that structure to that tess amount variable that we had. So we're just saying whatever that slider was, set that as the tessellation value, and we're good. Okay. The next stage, this is the actual meat of the hull shader. This is the function that's going to be run per control point and acts as the main function for the hull shader. And you can see, actually, there's an interesting line of code, a bunch of lines of code up at the top here. For those of you who are not familiar with HLSL, these are called attributes. You might see them if you've written any C# code. We use them in slightly different manner. This is to define parameters of the pipeline that are just sort of fixed. This is actually mostly data that we're going to feed down to the tessellator to tell it what to do. So we say that the domain is quad, meaning it's a quad patch. We say that we're going to be doing a partitioning scheme, and we've actually used a macro here to define it so we can switch between a couple different ones. We have the output topology, and what this is saying is we're going to output triangles, and they're going to be clockwise oriented triangles. So this is actually really the common case. And the next line of code is what the size of the patch is going to be for output, so how many output control points we have. Again, we're using a defined value up at the top of the file. Then the next one is interesting. Remember that function that I told you about that figures out the patch constants here? This one here, Bezier constant HS? That's actually provided here as the patch constant function. And this is a function that will be run once per patch, and will figure out the values that are needed across the entire patch. Because this Bezier HS function, the one that we're defining here, is operated per control point. And you can see this is actually a very simple pass-through of just taking each control point that is its input and outputting the exact same value. Again, this is just another pass-through because all the control points don't need to be modified at all. Okay, the last one here that's a tessellation-related shader is the domain shader. There's a lot of code here to actually do the Bezier evaluation. This is actually really great code to have in a sample. You guys can totally rip this off if you want. And essentially, we're doing Bernstein basis Bezier evaluation. So we have a bunch of helper functions that let us do that. And then finally, when we go and call the actual Bezier function here, this is the domain shader, we take in all of the control points that are available, the UV coordinate of the current tessellated point on the patch, and we're going to provide some output, which is going to be an XYZ position. So then we do all of our math to figure out exactly what the Bezier points are going to be. We do the world multiplication here using that view projection matrix, and then we can finally return an output. So now we've converted this high-order patch by stepping through each of these stages into an actual set of triangles that we can render. The last thing that we're going to do is we're going to execute a pixel shader to actually render the shading for this. And we have two examples. We have this idea of the actual wireframe overlay. So this just returns a solid green color so that we can get the nice green wireframe that we have available. And then the other one actually does the real shading, that sort of red, smooth velvet shading. And this is just done using a dot product fall off based on where the camera position is. So this is very simple sort of Bezier fall off of what that value looks like. And if I rerun the code, you can sort of see what this all gets put together. So this is using that nice smooth shading algorithm I have, and then if I toggle the wires, this is the green shader that we have. And you can see we're passing that value in, and you can see how each of these shader stages runs. Okay, back to the slide deck. This is a lot of information. I've said this before. We're really bare bones here. We're very, very customizable. There's a lot of complexity in the way that we introduce features in Direct3D 11. But it's worth it because now you can target almost any algorithm you want. Keep in mind that I actually had to define the Bezier function for exactly how I wanted to evaluate. This enables me to do anything I want in this pipeline. And there are a bunch of different algorithms that we're seeing people do today. A simple example of one is where you pass through everything just to the domain shader. You just don't transform any of the data. In fact, all your control points, you just provide 4. You just provide your patch. But you also provide a texture map, which is just a value from 0 to 1. And then you can determine the position of each vertex based on sampling that texture map. And now you have a way of doing very high detailed tessellation algorithms by providing a texture map instead. So we call that displacement mapping. And you can mix and match these things. I could use something like displacement with the Bezier system, and I can get smooth surfaces that have fine-grained detail. We have different algorithms that are used in CAD and CAM software that we can touch upon. An example of this would be something like NURB surfaces. So a NURB surface is non-uniform rationalized B-splines. It's a more advanced, more mathematically capable system for being able to render higher order surfaces that's used a lot in the CAD world. A lot of these things are available in 3D software for creating 3D models, and now you can take these types and you can render them in real time on these graphics cards, which is really incredible. Another thing that's worth noting is we can turn on and off the idea of dynamic or static tessellation. We can turn on and off a bunch of different features. Dynamic versus static tessellation would mean generating all those triangles on the fly or caching them onto a vertex buffer and then just using them over and over again instead of kicking off the tessellator. Another opportunity we have is, remember I was talking about dynamic tessellation, so changing my tessellation factors? If I don't want to do that, if my models are roughly in the same space for my entire application, which could be the case in your application, we can throw away all the code for doing that dynamic determination. So we can really specify the pipeline down to the minute details that we need. The last thing I want to talk about, I went backwards instead of forward, sorry about that, is this idea of subdivision surfaces. And you can actually see surfaces walking through a subdivision algorithm here. And essentially what this is double the complexity, so make double the number of triangles, and then do some smoothing over those to make it an even more smooth surface. This is called Catmull-Clark subdivision. It's used very widely in the movie industry. So pretty much any movie you see with CG, they use Catmull-Clark subdivision surfaces to create their models. This was innovated at Pixar, and there are a lot of assets available in this. With the graphics pipeline, we have these incredibly high-quality assets available now to us, using this hull shader to convert a subdivision surface into something that the GPU can use very, very quickly, say the Bezier patch system that we used earlier for the Mobius strip, to get a low polygon count when we need high performance, to get a high polygon count when we need refined detail, and get performance and quality trade-offs that we could never get before in real time. And one of the coolest things about this is that we have this idea of being able to do round tripping, or the idea that I can be using these assets that were previously available, and rendering them in real time, seeing exactly how they render on the real time display, and being able to edit them live, sort of send them out to a digital content creation application, modify them, and then immediately see the result and tweak it. But for this to really be available, we need to make sure that the industry is providing something for us that enables us to be able to interoperate with the digital content creation tools. Again, I keep hitting the back button. So one of the things I'd like to feature today is this idea of the FBX format, which just recently provided additional support in its latest version for the tessellation formats in Direct3D 11. So what this means is now we have this subdivision surface that we've been defining before available in a very popular interchange format across CAD, CAM, and 3D modeling software that you can now output the data in these higher-order primitives, never convert it into triangles, load it into Direct3D 11, and be able to render it immediately. And then you can take data that's being used in DirectX 11, pull it back into your digital content creation application, and be able to modify it. This is a really big step in being able to make sure that these formats are available to the entire pipeline for art and production in your application. So the last thing I want to show today, in the few minutes that I have left, is an example that really brings together a lot of what I've been talking about today. It brings together the concept of subdivision surfaces, of real-time rendering, dynamic tessellation. And this is a demo that we've shown in a couple places, but I'm really excited to show it now to you in hardware. And this is what we call the Sebastian demo. I'm going to go ahead and switch over to the demo machine. We had a little naming contest internally to figure out what his name would be. And we decided on Sebastian. And it's this steampunk character, as soon as he loads up. Here we go. And right now we have him rendering so you can see the tessellation. Let me turn that off so you can see the actual 3D model. What we have here is we have a model that right now is actually at a pretty low tessellation amount. I've actually turned off all tessellation, so now you can see some of the jaggedness. And you take a look at his face, take a look at his arm. You can see that it looks, this is essentially what Direct3D 10 models looked like before. It's sort of this, it's still a pretty high quality experience, but you can see that a lot of the detail sort of gets jagged. You get these sort of harsh edges as he moves around. Well, I'm using animation here on the control mesh, so I can go ahead and just start jacking this up, and you can immediately start to see the detail improve. Really, to see the benefit of this, I'm going to go ahead and render it in wireframe mode. And you can see we're going from this pretty low-end model here. This is just the lowest tessellation set. And we can just keep going and going. And it's pretty incredible what kind of tessellation you can get with this. I mean, the number of triangles that we're rendering here is pretty sophisticated, and you get the best quality content you want. This demo is using pretty much every single technique I've talked about today. It uses subdivision surfaces. It uses some kind of texture displacement to get some detail values across his leather jacket and his face. In fact, this bump height is actually what turns that on. So I can actually blow this way out of proportion if you want to see exactly what it's doing. And so you can still see that it has this amount of tessellation available to it, but now it's using a texture map to actually figure out those values. And yeah, it's dynamic. I can change the exact amount of tessellation that I have available, and I have a really high-quality rendering system doing some cool lighting effects too. So this brings it all together. I encourage you guys to check out everything that we have available in the DirectX SDK for this. I'm actually going to go ahead and jump back here and give you a resource slide so you can see everything that we have. One last thing I do want to note is the platform update for Windows Vista. Remember I said that we had multi-threading on G3D11 available on Windows Vista? This is how. Very proud to announce to tell you about this. This was actually announced a couple months ago, but we have this new Windows Update package available now called the Platform Update for Windows Vista that provides a large plethora of technologies that are available in Windows 7 down on Windows Vista so that you, the developer, can utilize those things on the broadest number of systems that are available. This includes things like DirectX 11, improvements to Direct3D 10.1, Direct2D, DirectWrite, some improvements to DXGI, and then a host of other things outside of the DirectX pipeline. And I encourage you to go to this KB article to learn more about it. Here's some, I don't actually want to go to the KB article right now, but you can learn more about it from there. Sorry for the click. And here's a slide with some additional resources. The DirectX MSDN site, check that out. It provides some links to the MSDN documentation as well as some white papers and the code samples. The Windows 7 SDK, and then finally the August 2009 DirectX SDK, which contains both of the code samples that I showed. You can download this and check them out today, as well as a bunch of the documentation around Direct3D 11 and what you can do with it. So that's my talk. Thank you very much for coming. Your feedback is important to us. I want to remind you, I think we provide $1 to the Boys and Girls Club of LA for every survey that you fill out. So please go online to Microsoft PDC and check that out. Thank you very much. And of course, these videos will be available on Channel 9. So I'm going to open up the floor for questions. Please approach the mic. I've got about 5 minutes for questions, and then I'll be able to talk to you out here. And I should be in the big room afterwards during the Ask the Expert session. So come and talk to me there, too. Thank you. Are there any questions? Come on, anybody? OK. Thanks a lot, guys.